This assessment asks us to draw the most stable chair conformation for the tri-substituted cyclohexane shown. To make this easier, I've gone ahead and numbered the 6 carbons of the cyclohexane and drawn the first chair using those same numbers. Now, the numbering here is not meant to be IUPAC numbering, they're just labels, and we're going to see then how these labels transfer the structural information from this structure into our chair. Which chair did I start with? Once again, that was also arbitrary. Here's where the arbitrariness stops. At carbon 1, you'll notice that the tert-butyl group is on a bold wedged line. That implies that it's coming towards us, and keep in mind, I'm looking at it from above the ring, even if in this video it looks like I'm looking at it from behind. That would be the equivalent of me looking at it from here. So we're going to imagine an eyeball looking down. So if that bold wedged tert-butyl group is coming towards me, then it also needs to be coming towards the eyeball. And so for that reason, it's going to be axial at carbon 1. Let's go ahead and draw on the equatorial hydrogen that would be going away from the eyeball. There's nothing at carbon 2, nothing at 3. When we get to carbon 4, we have an isopropyl group. Now this is on a dashed wedge bond, which would imply that it's going away from the eyeball. So we have 2 substituents, equatorial kind of going up and towards the eyeball, and the axial going down and away from the eyeball at carbon 4. For that reason, the isopropyl group is in the axial position. The hydrogen is here in the equatorial. The same thing at carbon 5. This carbon 5, the ethyl group, is on a dashed wedge bond, which means it should be going away from the eyeball. To go away from the eyeball at this carbon, the axial substituent goes towards the eyeball. The equatorial substituent goes away. And so we can draw the ethyl group in the equatorial and a hydrogen in the axial. From here, we're ready to do the flip. Let's do that by taking flap 4 up and flap 1 down. That will generate the flipped chair that looks like this. Keeping the numbering, this will be carbon 1, carbon 2, 3, 4, 5, and 6. Note that at carbon 1, what was axial and up will now be equatorial and up. The up doesn't change. If it's up in this structure, it must be up in this structure for us to have done a real ring flip. Moving over to carbon 4. At carbon 4, the isopropyl group was down and axial. Now it will be down and equatorial. The up-downness doesn't change, but the axial changes to equatorial when we do a flip. At carbon 5, we had equatorial and down. Now we will have axial and down. Let me move that number 5. Axial and down will be our ethyl group, and our hydrogen will be in the equatorial and up position. And so we've generated the second chair. With both chairs, we can now decide which one we think is most stable. Note that the one here has an axial tert-butyl, an axial isopropyl, and an equatorial ethyl. 2 axial groups and both large axial groups. That's not good. Down here, this one has an equatorial tert-butyl group. That's good. Equatorial isopropyl, also good. The ethyl group being in the axial position, we'll take it. If it allows us to have our largest groups in the equatorial position, then we can accommodate small ones in the axial position. As a result, this is our most stable conformation of the tri-substituted cyclohexane.